stealth technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window onto DARPA's core of program managers. Their job, to redefine what is possible. My name is Ivan Amato, and I'm your DARPA host. Today, I'm pleased to be talking with Dr. Tom Rondeau, who joined DARPA as a program manager in 2016, first in the Microsystems Technology Office, MTO, before transferring into the Strategic Technology Office, STO, in May. We are recording our conversation from our respective homes as we do our part to slow the spread of COVID-19. Because we are not in a recording studio, you might hear ambient sounds like trucks or trains. Let me tell you a little bit about Tom. Earlier in the millennium, he collected 3 electrical engineering degrees from Virginia Tech in Blacksburg, earning his PhD in 2008. Several years before that, he got seriously involved with the GNU Radio project. That's GNU, like the animal, which is an open source haven for radio hackers, makers, and others interested in using software modules to do a wide range of radio anchored tasks, such as communicating with satellites or controlling household drones. As a visiting scholar at the University of Pennsylvania and as a research scientist at the Institute for Defense Analyses Center for Communications Research in Princeton, New Jersey, Tom furthered those causes with his work, among other things, on architectures and algorithms in signal processing for communications and the monitoring and use of the electromagnetic spectrum. Tom is as much of a community builder as he is a tech guy. He has organized many conferences and workshops and has been spreading the word like an evangelist on new technologies in wireless signal processing, among other radio techniques. Tom's current interests include adaptive and reconfigurable radios, improving the development cycle for new signal processing techniques, and creating general-purpose electromagnetic systems. Tom Rondeau, thanks for joining me in this conversation.
Yeah, thanks, Ivan. It's good to talk to you.
So before we dive into your portfolio of DARPA programs, which range from software-defined radios, and we will explain that a little later, to a new category of powerful yet affordable chips for specialty computation-intense applications like signal processing, let's give listeners some sense of how radio technology became your thing.
As you mentioned, I got all 3 degrees from Virginia Tech down in Blacksburg, and what happened was I'm kind of intellectually restless, so I was also getting a literature minor in English literature. One of my English professors, I think, realized my restlessness, put me in touch with Charles Bastian, who was a professor of electrical engineering, but his wife, Frida, was a member of the faculty of the English department. So there was kind of this connection there, and I frankly just walked into Charles's office, Dr. Bastian at the time, and said, as a sophomore, said, hey, I'm kind of bored. I'd like to do more while I'm here, make the most of my university career. I was more involved in like processors and networking and just kind of how to make computers talk to each other. And Charles is a wireless guy, and we kind of combined those and started really looking at wireless networking. So he kind of took me on as a test as a sophomore over a summer period, and was impressed enough that as I was doing some Bluetooth work, this is back in 2000, so early in the Bluetooth era, impressed enough that he kept me on. I kept working in the lab, doing more stuff with higher frequency stuff and radio propagation stuff, and then eventually that turned into a master's degree, and he kept me well funded and I guess just well engaged with wireless stuff all the way through my PhD.
Wow, beautiful. We should all have such mentors. I always love when I hear about, teachers and individuals, adults in our lives who really have had transformative effects. So it sounds like this prof was that person for you.
Yeah, mentor is the right word to use for him. The number of things beyond just the skills as a researcher and as an engineer that I learned from him, how to deal with people, situations, just how to behave as a adult in the field, as an engineer that's doing more than just the core work. He was great for that.
Okay, and so what happened along this trajectory, and as this interest of yours developed and intensified, is you became very much involved in the GNU Radio organization. So most people, I think, listening might not know what that is about, and so I'd love you to just say briefly what is the GNU Radio project, and then I'd love to know what catalyzed the leap from there to DARPA.
GNU Radio is a free and open source software framework for building software-defined radio capabilities. So what is software-defined radio? It is the ability to program in your computer signal processing techniques, so math, applying math to signals that manipulate the electromagnetic spectrum. And so what we say here is that the electromagnetic spectrum or electromagnetic waves are one of the four fundamental forces of the universe. And what software radio allows us to do is write programs that manipulate one of the four fundamental forces of the universe. And once that thought really hit me and hit a number of us in this field, that was that kind of awe moment of all of us going, this is incredible. This is breaking open and making accessible to us and to hundreds of thousands of people around the world their ability to access and control this thing that controls our, as you mentioned, drones, satellite, all of our cell phones. Our utility systems are now all connected and communicate wirelessly. And it's just a rich field that is rooted in this. And GNU Radio is this tool that allows us to make that happen in the real world.
Now, Tom, so you mentioned the word awe. You were having a kind of awe moment as you were thinking about the electromagnetic phenomena in the world and how you can actually interact with it. So this reminds me of something, and I want to get the timing of it. You have on your arm or arms tattooed the famous four equations from Maxwell, Maxwell's four equations that describe electromagnetic phenomena. Was it at this time that you were moved to get those tattoos?
Yes, it actually was. It was thinking about those four equations, as you say, Maxwell's equations, and that shows us as something that we as humans have done, which is understand this incredible force and what it does for us, codified in these four, in some senses relatively simple, but then when you break them down, they're very complicated equations. And so, yeah, they're tattooed. I got two each on each forearm. And I look down at those every day and have that moment of awe of what we've been able to do.
Right. And to me, that is one of the best metaphors of the kind of devotion you often see to science and technology by program managers like you. So very cool. The second half of my question here was, so you described GNU Radio. What is it then that got you to DARPA?
And what happened was in 2015, I met Bill Chappell, who was the director of the Microsystems Technology Office. And he invited me to a big DARPA event called Wait What that was showcasing a lot of DARPA capabilities and technology. And he wanted me to come and talk about Spectrum. Now, this wasn't my first interaction with DARPA as a grad student in electrical engineering, especially from a school like Virginia Tech. We're well aware of DARPA. It's part of our funding source. It's part of our growth in the research community. So I met Bill, and it was always in the back of my head that I'd love to go to DARPA. I'd love to be the kind of person that can make the contributions to the technology of the country and larger than that of the world. And that's what DARPA, always represented to me as the most impressive, cutting edge. It's where all the cool tech comes from. So it was always in the back of my head that I was going to do this, but I never felt ready. I met Bill and I figured, you know what, whether or not I'm ready, I'm never going to think I'm ready. It's time to step up and take the opportunity to see about getting into a position like this. So I asked Bill and he said, let's try it. But the reason why I wanted to do that, back to the root of the question, was that elevation of focusing on this project, GNU Radio, which is wonderful, but I had this inkling that I wanted to be able to affect more. And that's the opportunity that I saw at DARPA, was to, instead of just coding, I was able to organize and really put real resources behind some of the ideas that were in the back of my head of what I wanted to accomplish and what I thought technology could become. So I jumped at an opportunity. It was May of 2016 when I got to sit down for the first office meeting with these incredible other program managers and kind of realized how in over my head I actually was. When you meet your fellow peers at DARPA, it's pretty awe-inspiring. Back to that word again.
You might have been in over your head for a while, but you sure did come to embrace the job and really become quite the PM with quite an amazing portfolio. And that's what I want to get into now. So let's take a tour of the fascinating programs that you have been overseeing, initially at MTO and now at STO, those two of the 6 DARPA technical offices. Let's talk briefly about 2 programs that seem related. One goes by the name Domain-Specific System-on-Chip Program, and the one that seems related to me, but you'll clarify that, goes by the name Software-Defined Hardware. So talk to me about those and what you hope to achieve with them and what the status of those programs is.
Those are two great programs. I was able to formulate the full domain-specific system on chip, or DSSOC program, and then I worked closely with the other program manager who crafted the SDH program, Software-Defined Hardware. But I've been running that program for the past year when he left the agency. To people unfamiliar with Software-Defined Radio, it might seem weird that I went to DARPA and started running processor programs. But that's what the software-definedness really means, is that we're programming the radio spectrum, and the more you want to do, the more processing power you need in order to do all those cool signal manipulations that make satellite communications work, that make 5G technologies work. So new processors are core to making this happen. DSSOC, it was all about trying to understand how to overcome the limitations of general purpose embedded computing. What I mean by that is taking your general purpose Intel processor. What's cool about that processor is it can do almost any mathematical computation you can think of. It doesn't necessarily do any of them particularly well, but we were able to use that as our programming platform for all of the GNU Radio work. So we were using and slightly misusing this great general purpose processor. But what we realized is, every generation of a processor coming out, we'd be able to do more because you can do, they're faster, they're lower power, all those cool things that were coming with Moore's Law. As you start to see some of those, the node size or the feature sizes of these transistors starting to come to the end of the line as far as just free processing power in next year or 18 months or whatever. And so, stealing from Winston Churchill, we realized the money's run out, it's time to think. The transistors are running out, it's time to think. What do we do? How do we kind of shift laterally in our thinking? And coming at it from the signal processing world was like, hey, there's a lot of math that we do over and over again. What if we built a hardware accelerator that did just that math? But then we tied it onto a system on chip, so lots of these different cores that all work on the same silicon chip packaged together, that we could kind of balance this general purpose processing and special purpose computation to be able to accelerate those core math problems that we keep running into. If we can make use of that, we get to accelerate our ability to control of the electromagnetic spectrum. So that was the core impetus. Now, the second part about DSSOC that's really important to me, and one of the key concepts of a new processor to me is, if you give me a new processor without code, without a compiler, without a way to use it from software, you've literally just handed me solidified sand, and that's all it's good for. So coming at it from that perspective, DSSOC is also about the software tools. How do you actually make use of what we now call a many-core heterogeneous computation system? So we can have dozens of cores, each one of them doing different jobs more effectively than others. How do you distribute the software down onto a chip like that without it becoming a massive burden to the developer? We couldn't rely on these general purpose processors to give us the speed. So we're kind of balancing those out by having some special purpose and some general purpose, and taking advantage of the small transistor node sizes that Moore's Law has produced. And I say Moore's Law, but really the hard work of the entire silicon industry has produced for us, and then make it programmable.
That program sounds like there's really a hardware component, or it might be hardware-centric in the sense of specific modules, whereas software-defined hardware sounds like you're using software to get specialty out of the hardware.
Yes, and the core distinction here is every engineering problem is a trade-off. And what we're saying in both DSSOC and SDH is you can get programmability and high performance in the same chip. And currently those are competing objectives. So you normally can't get both. You can get high programmability in the general purpose processor, high specialization and efficiency in the ASIC. We're saying that you can actually get both, but we're giving up something. So we're not going to replace the Intel processor in your workstation or your laptop. What we're going to do is create different types of architectures that meet different needs. And in my case, the DSSOC need was embedded processing and really hyper-specialized math processing on these signals or video or images or whatever. What SDH is asking is a different context of problem, of space for problems, big data. machine learning, large data sets. We're talking billions, trillions of bytes of data, or billions or trillions of images, or social networks, or whatever we're trying to understand and compute against. The challenge with that kind of computational model is moving data in and out of the processor. That's typically our limitation. Often our processors are bored waiting for data to be delivered to them, and then they crunch on it really fast, and then it takes them a while to offload that data back into memory. Software-defined hardware is how do you have software programmability of the memory access models in order to make sure that you're balancing the data movement and the computation efficiently, and again, without overburdening the programmer for trying to specialize to this new architecture. So that's the similarities and the subtle distinctions between the two.
Let's segue to another program that sounds a little bit like software-defined hardware, except this one is called SoftwareDefined Radio 4.0, and I think that might actually have roots that go back a way for you. So talk to me about that.
Yeah, so software-defined radio, or SDR 4.0. This is, again, thinking about DSOC as a new type of processing framework, an architecture and programming environment for doing things like software-defined radio processing. But then we had GNU Radio, which was designed to take advantage of these general-purpose Intel-type cores. We needed to bridge that gap. And so what we're thinking about with SDR 4.0 is how do we make a general programming environment like GNU Radio able to target heterogeneous processors. And the reason why is because, as I mentioned, general purpose processors can do anything, just not particularly well. But then you have other processors, like a famous one right now that everybody talks about is the GPU, the graphics processor unit. A lot of machine learning is now done on GPUs. They're good for what we call dense linear algebra. There's a lot of problems that are represented as dense linear algebra problems, and those are offloaded to GPUs really well. Then there's other things like field programmable gate arrays, or FPGAs. Those are really good for high throughput, high I/O input-output processing problems. Each one of these has a role to play in different stages of processing an entire signal. Well, GNU Radio had no idea how to take advantage of those effectively. So we've been looking at this problem for a while, this heterogeneous processing problem. I said, well, look, DSOC is coming along, and we're doing, frankly, amazing stuff in innovations down there. But we also need the software programming environment that can take advantage of existing heterogeneous or even future heterogeneous type processing environments. So then if I take a look, we take a step back, and I think about, because I'm also a history nerd, as the Maxwells Equations probably clued you into. But going back, even into the 70s, people really started to start programming in these digital signal processors, or DSPs. That was kind of the early stages of what became software radio. And then in the 90s, there was this thing called Speakeasy, and this was actually a DoD-funded project to create this machine called Speakeasy that was like the first software-defined radio. So that's kind of generation 2 of software-defined radio, is when we really codified what it meant to process all the signals in computers. And then GNU Radio, I think, represents today what the third generation is, which is this more dynamic, flexible processing stage of the signals. And so we're saying, okay, what's next is let's do good processing with programmability, and mixing those together with that heterogeneous processing nature of all the processors. That's the fourth generation of software-defined radio. So that's what we're trying to do, is make these things both, flexible and programmable, but also take advantage of the efficiencies that different types of processing elements provide for us.
All right, so to finish out this tour of the research that you are overseeing, talk to me about a relatively small effort, I think it is. It's called Hedgehog.
It is a small effort in DARPA terms, but it's at a really key place in my heart as a DARPA program manager. This is a new embedded device that makes software-defined radio practical. All right, so what I mean by that is to communicate to this radio spectrum, the electromagnetic spectrum, you need to have the ability to transition between the RF waves and the digital processors that we're programming.
Right, the radio frequency waves and the processors.
Yeah. Mm-hmm. So what we're trying to do with Hedgehog is take advantage of DARPA technology, one that we ran in a program called the RF FPGA. And that program, it's a long acronym, but I talked about field programmable gate arrays before, FPGAs. Those are digital processors that can be reprogrammed to do a lot of things. What RF FPGA said is, can we do the same thing with analog signals? Can we have a programmable array of signal processing, amplifiers and mixers and oscillators and filters? These are important building blocks for communicating, transmitting signals into the spectrum or receiving signals and capturing them. So I inherited that project when I came to DARPA. We also were investing in work with Xilinx to create a new type of embedded FPGA processor, which had embedded analog to digital and digital to analog converters. Now those are the actual blocks that move data between the digital world and the analog world. So we thought, if we could combine these RF FPGAs with this embedded processor with the integrated converters, that is a really amazing package that creates an embedded software-defined radio platform for us. It'll host its own operating system on the processor. It'll do the digital signal processing portion of the FPGA, and it talks to this RF chip, these RF FPGAs. Now, the really interesting thing about this, and why we called it Hedgehog, is because it has multiple channels. So you could connect 16 antennas to a Hedgehog device. And the fun thing is, this is in the electronic world, this is called an array. You might hear of active electrically steerable arrays or phased arrays. There's a lot of talk about that, especially with 5G. The more antennas you have, the more it becomes an array that you can manipulate. Well, it turns out that the collective noun for hedgehogs is an array. So that's why I named it Hedgehog, was because I thought that was fun. But the other really cool thing is, not only is it a multi-channel digital beamforming system, or multi-channel, multi-function, because every antenna could be doing a different function. One could be scanning the spectrum for signals, for interference. One could be communicating to a cell tower. The other could be communicating to a satellite, frankly. So that's really cool on its own. The other thing that we're pushing on in this system is the traditional commercial software-defined radio system, the bedrock of all of what we do. But they're typically limited to about 6 gigahertz. And what 6 gigahertz is important is that's where most terrestrial communications happen. So your TV, analog, over-the-air TV, AM, FM broadcast, most cell phone up until 5th generation, all cell phones up until 5th generation, are under the 6 gigahertz. So 6 times 10 to the 9 cycles per second. That's great. But what's happening now in the world is more people are trying to push into those higher spectrum, the higher frequencies. In the US, the 5G high band, as they call it, you'll also hear it called millimeter wave. Those are up at 28 gigahertz, 37 gigahertz, 39 gigahertz. Those are some of the new bands. Those are well outside of what most people have access to. And so Hedgehog is actually pushing up to cover 40 gigahertz. So you could tune this thing up as high as the high band 5G signals. And why is that important to me? This kind of goes back to the GNU Radio Foundation. What we did in GNU Radio was really broke open this access to the electromagnetic spectrum for people to change how they learn what signals are, what radio waves are. We teach things differently now because of this type of technology. Millimeter wave signals behave differently. They bounce off of things. They don't penetrate things.
This is the range of waves, the millimeter waves that you're talking about, up at that sort of 40 gigahertz area,
the
right?
30s up to 40s, yeah, that type of stuff. Those are these high band millimeter waves. So they behave differently, and we don't have the tools to access them and really have that level of engagement that we do at the lower bands. And so we're hoping that we learn through kind of collective research and just being able to have more researchers do more, and that flexibility of programming the spectrum and changing the way that they engage with the spectrum, maybe hundreds of times per day, to tweak, to tune something, to see how things behave differently. That's the level of access that a device like Hedgehog is going to give us to this type of spectrum, this unknown space that we're trying to operate in now.
Okay, so just a couple of things on that. One is it's very interesting to hear how you're making it possible to crowdsource investigation in areas of the electromagnetic spectrum that have not really been that accessible to as many people as this program will open it up to. So the question, though, is then how do you connect this to, say, the DARPA mission?
To me, the complexity of interacting with the electromagnetic spectrum is well beyond what we can do with the numbers and the resources that we have within the DoD. And so for us to take advantage of it, we really have to engage the wider community and learn from them and build a mass of research and a research body that can help us tease apart what's really important, what's not, what's effective and what isn't. So we're balancing the need for, technological superiority and surprise, but with building up better understanding and engagement with this incredibly complicated force that we use for all of our stuff.
Right. So we're getting to the end here, but you just made me want to ask you a certain question. As someone who has been so immersed in the electromagnetic phenomena to the point that you've actually tattooed Maxwell's equations on your arms. I mean, when you look out at air, at the atmosphere, you're bringing in a sort of radio sensitivity, radio kind of mindset, so how filled every little millimeter of air is. So it must be a kind of very rich thing to have that understanding. It must sort of enriches your sense of nature.
Yes, I absolutely think it does. The electromagnetic force operates on this level of visible light that we see through, of radio waves that we communicate, as I said, to satellites, to phones, to our wireless internet is all based on it. It's in this sweet spot for us to use, manipulate, and embed information. And so we can move, this is how we get all of our information moved around the world, is through the electromagnetic force. That's the key. It's not just playing with waves for the sake of playing with waves, but it's connecting information and moving information around us. So when I think about that, what you just said, that kind of poetic sense of the world being surrounded by electromagnetic waves, what I really see is this interface of information, which has been important to us as society to move our stories around, to move our friendships around, to our economies. All of that's embedded in this force in some way. And again, that's what we're trying to help understand better and expose and let more people help work with it.
Nicely said. And I just actually have now one more question before we really close out, and it has to do with the Internet of Things. This is the billions of various gadgets, small and large, that are striving for access, to the electromagnetic spectrum to give or receive signals, sensor signals, to get GPS signals and geolocation data and all kinds of things. And the second right now, there's probably another 10,000 of these Internet of Things gadgets that just went online. So when you think about that explosive growth and the programs, sort of the themes of your programs, what's the interface there?
It's been since the 3G, like since the 90s, since the world has been this excited about wireless technology. And part of it is IoT, because all those devices need to communicate over the spectrum. And I don't go so far as to say the spectrum is a scarce resource. It is a renewable resource. It's not like if you use 1 hertz, it's gone forever. You can reuse it, but it does become congested. It does. They do step on each other. What we call interference. In the military terms, we call it jamming. All these devices communicating, this understanding of the electromagnetic spectrum, so just thinking about it from the ability to see and engage with the electromagnetic spectrum, is one of those things that's going to be necessary for us to tease apart these challenges of making these billions of devices work and communicate together. The second thing is all of the processing that we do. The way to be what I like to call maneuverable, being maneuverable in the spectrum, changing frequencies, changing waveforms, avoiding other signals so that you can communicate. All that stuff is going to take processing power. And all these IoT devices, or many of them, aren't connected to wall power. They've got batteries. So you have to build better, more effective processing capabilities, the processors themselves, the radios have to be more efficient, our programming and our applications use of those sources. Power is the scarce resource here. And so that's those two key aspects here of how do we use the radio spectrum efficiently, and how do we manage our battery lives on these edge processors, these edge devices that are battery powered. Both of those you can see themes of in the programs, between the embedded processor DSOC program to the Hedgehog program to SDR 4.0, trying to make kind of combine a lot of that stuff.
Wow, Tom, so you really are on the forefronts of many of the most important technological trajectories of these times. It must be real exciting. So, I mean, we're getting kind of to the end of this. I just wanted to give you an opportunity to let me know what question I didn't ask, and you're appalled that I didn't ask it. And if there is a question like that, ask it and answer it.
Real quick side note, we're in the middle of contracting for a new program that we call Data Protection in Virtual Environments. And this is creating a new processor to solve a hard cryptographic problem to allow us to compute on encrypted data. So now think about all of your personal data that exists in the cloud or on other servers somewhere. If it's always encrypted, then data leaks start to become a thing of the past.
Oh, it's a gorgeous program, because all of us are super anxious about the integrity of our data, but we also know that if we can use this data freely, we might be able to really discover important things.
Yeah. And so that, in my world of thinking about RF and processing, and it all coming around to really it's about controlling information, that leads me into the ultimate of how do we protect that information as we're controlling it.
So, Tom, we're out of time, but I have to thank you just for the whirlwind of a discussion where we cover so much of what you are overseeing as a DARPA program manager, but also just really enjoyed hearing you talk about your views on the history of technology and how it unfolds and all the twists and turns. Always fascinating to hear these stories of innovation. So thanks for sharing all this time with me.
Thank you. As you can hear, I'm pretty excited and passionate about this stuff, so it's wonderful to talk to you, and hopefully people will find this interesting.
We all benefit from those kinds of passions, and then when you bring the kind of expertise you bring to it, the world will potentially, quite likely benefit from it too. So thanks again. And thanks, listeners, for sharing this time with Tom and I. I hope you join us again for the next Voices from DARPA. Thanks also to Ben Sullivan for his partnership in producing this program. For more information about Dr. Tom Rondeau, the programs he runs, and the other breakthrough technologies DARPA is working on, visit darpa.mil. And for links that enable you to download this podcast, go to the Voices from DARPA page on DARPA's website.